In today's session, we'll be discussing about the unit commitment solution method using the dynamic programming approach. So what is this dynamic programming approach and why we should go for this dynamic programming approach and what is happening in this dynamic programming approach we'll discuss. So this is about the unit commitment solution method so that you should understand. So why we go for this dynamic programming approach is there is one important advantage. What is that is there is reduction in dimensionality of the problem. So what is this reduction in dimensionality of the problem that you should understand, or how this reduction in dimensionality of the problem is evolving. So for example, if there are 4 units in an area and any combination of them could serve the demand. Why I am mentioning here it as single means for a given R. So if there are 4 units in an area and any combination of them means either 1 unit alone or 1 and 2 or 1, 2 and 3 or 1, 3 and 4. Any combination, that is what is meant by any combination of them could serve the demand. That is, we are going to take an R or a period. So this single means a period. So we are going to take a period and we are going to meet the demand using any combination of these 4 units is that you should understand. So if there are 4 number of units, there will be 2 power 4 minus 1, 15 combinations are possible to test. But if you impose strict priority listing or strict priority ordering using the full load average production cost, which we have discussed in the priority list method, there will be only 4 combinations to try. So if you can see here, from 15 combinations, it is getting reduced to 4 combinations. That's why we say that there will be reduction in dimensionality of the problem. So there will be only 4 combinations to try. What are those 4 combinations? So out of those 4 units, you will assign priority 1 to a unit which has the least full load average production cost. So you will have a priority listing or priority ordering in which you will assign a machine with the least FLAPC to be priority 1. The next will be the priority 2 machine, the next will be the priority 3 machine, and the last will be the priority 4 machine. So either with only 1 unit which has the highest priority you can meet the demand, or with 2 units which has got the priority 1 and then the priority 2 you can meet the demand, or with unit 1, unit 2 and unit 3, that is unit 1 plus unit 2 plus unit 3 in strict priority ordering you can meet the demand, or priority 1 unit, priority 2 unit, priority 3 unit and priority 4 unit. You can add all those 4 combinations and you can meet the demand. So the answer for this reduction in dimension of the problem is, if you go with this ordinary thing, that is 2 power 4 minus 1, you will have to try with 15 combinations. There will be 15 combinations to test, and if there is some 8 hours to test means then you should check it for 15 to the power 8. So you can imagine how large the number of results will be. So that is not needed if you go with this strict priority ordering. So there will be reduction in dimensionality of the problem. That is the first thing you should understand about this dynamic programming approach. First thing. Second thing is we are going to impose a recursive algorithm. So what is this recursive algorithm? We'll discuss. So before going into this recursive algorithm, let us consider an example problem so that you can understand it better. So let us consider a problem in which, let us consider an example in which we have 4 units. So we're going to take 4 units. So units 1, 2, 3 and 4. Their maximum capacity is given. Say for example 80, 250, 360 megawatts. And the minimum limits is given 25, 60, 75 and 20 megawatts. And the load pattern is also given. See, this is the given R and this is the load that is required during that hour. So in the first hour the demand is 450 megawatts. Second hour 530. Similarly, if you go on in the 8th hour it is 500 megawatts. So this is a problem where we have 4 units with the minimum and maximum capacities, and you have this load pattern that is being given. And let us assume that by FLAPC we get the priority order of the 4 units. Let us assume that unit 3 is operating at a lowest production cost. So the full load average production cost of unit 3 is very minimum, and comparing to the other 4 means then you can assign the priority listing or highest priority to unit 3, and suppose the FLAPC of unit 2 is less when compared to 1 and 4, you will put unit 2 in the priority ordering next, and then unit 1, if its FLAPC is less than this, then you will put this in this ordering, and then unit 4. So let us assume that the priority ordering comes as 3, 2, 1, 4. So this we have already discussed. How to arrive at this priority listing we have already discussed in the previous session. Now you write the unit combinations from 0000 to 1111. So you have 4 units. So you write 0000 and 0001, 0010, like that you order or you arrange up to 1111. So if you write this ordering from 000 to 1111, 0 means the units are uncommitted and 1 means the units are committed. So compute the maximum capacity for all the 15 combinations. From C, if it is 000 means no unit is committed. What you will get? You will get 0 megawatts. Am I right? So if it is 0001 means how much you will get? Say for example, I am taking this as unit 1, 2, 3 and 4. So I am assigning 0001 means it will be 1 here, means the 4th unit alone is committed, means you will have 60 as the maximum capacity for 0001, 60 megawatts. So similarly, you should write for 0010 like that. Which are all the units committed? You write the add. For example, if it is 1111 means all the 4 units are committed, means it is going to be 60 plus 300 plus 250 plus 80. You will get 690 megawatts as your maximum capacity of these 4 combinations put together. So for all 15 combinations, it will come from 0 to 690 megawatts. So that you should write. After writing this, you should go for what is called as the capacity ordering of the units. So after writing the 0000 to 1111 and then from 0 to 690 megawatts, after writing this, you go with the capacity ordering of the units. What is this capacity ordering of the units? Is you should arrange it in this descending order like this: 690, 630, 610, 550 like that. So you have arrived 0, 60 like that up to 690 you might have arrived, but this will not be in ascending order. That you should understand. This will not be in ascending order. This will not be in ascending order. So it will be a jumble numbers. But what we are going to do is we are going to order. Capacity ordering means that you should understand. You are going to order it like this: 690, and descending order you should go up to 0. So 690, 630, 610 like that you should go. So if you go like this, if you can see here, for 690 it is 1111. For 630 it will be 0111 like that. So this will get altered now, but this will be in the descending order now. Is it clear? Now you assign the states. So you assign the states. So you can assign it. This is 0 means 1, 2, 3, 4, 5, 6. Like this you can assign up to this. You will have 15. Altogether 16, but this is not going to be utilized. So you will have 15 states. So you write those 15 states in this descending order like this: 15, 14, 13 like that. You write up to this. So you can give the units numbers. So this is going to be unit 4, 3, 2 and 1. So this is what is called as the capacity ordering. This is very important. And if you impose strict priority listing, if you are imposing strict priority listing means, if you can see here, unit 3 has got the highest priority. So unit 3 you assign first. So if you assign unit 3 alone, 0010 means, if you can see here, 0010 means it is state 5 alone. So state 5 alone. For state 5, what is the capacity? Maximum capacity is 300. So next is unit 3 and unit 2. So unit 3 and unit 2. So unit 3 and unit 2. If you commit unit 3 and unit 2, so it is 0110. So 0110 is state 12. So state 12. What is the capacity? It is 550. So put that 550. Next is you are going to commit unit 1. So if you commit unit 1, it is going to be 3, 2 and 1. It is in this order: 3, 2 and 1. So commit 3, 2 and 1. So 3, 2 and 1 means it is going to be 3, 2 and 1. The state is 14. So the state is 14. What is the maximum capacity you will get? You will get 630 megawatts. So similarly, for if you are committing all this this 3, 2, 1 and then 4, it is going to be the state So if you can see here, if you are committing all the units meant, it is going to be state 15 and the maximum capacity is 690. So if you commit all the 4 units, the state is 15 and the maximum capacity is 690. So you should understand this. So you should understand what is a state and what is the combinations and what is the maximum capacity. So with this understanding, now we will go into this recursive algorithm to compute the minimum cost for the Rk with the combination I. So Rk means in the problem statement we saw the 8 Rs. Say for example I am taking the R to be 2, the second R. So in the second R, so we can see in the second R, the demand is 530 megawatts. For this 530 megawatts, what are all the feasible combinations that are possible is this state 12, 14 and 15 is feasible because 550, 630 and 690. This is not feasible because it is 300, but the demand required for the second R is 530. So the feasible states are 550, 630 and 690. So you should understand what the states are and what the R's are. So now coming into this, the recursive algorithm to compute the minimum cost. So we have to find the minimum cost. So that is our aim here. So minimum cost for Rk with the combination I. So what are the possible or feasible combinations you can test is, as you already seen, you can test for 12, 14 and 15. So the recursive algorithm is f cost of k, I is going to be equal to min of L P cost of k, I plus S cost of k minus 1, L is to k, I plus F cost of k minus 1, L. So this is what is called as the recursive algorithm to find the minimum cost for the Rk with combinations I. So for example, if you take for R2, if you are taking for R2 means k is equal to 2. So k is nothing but the R, k is nothing but the R. So k is going to be equal to 2 now. Feasible states, as you already seen, for R2 the demand is 530 megawatts. 530 megawatts. The feasible states are 12, 14 and 15. So why we say 12, 14 and 15? Because in state 12 we have 550 megawatts as maximum capacity, in this 630 and then in this 690. So these are all the feasible states. State 5 is not feasible because it has got only 300 megawatts in it. So X is going to be the number of states. Here the number of states are going to be 3. Feasible states are 3. This is very important. Suppose two strategies, 12 and 14, that is what is called as the L now, 12 and 14. This feasible, the strategies we assign N, which is going to be equal to 2, are saved in the previous stage for k is equal to 1. So this 12, 14 are the two strategies which are saved in the previous stage. Previous stage means for k is equal to 1. Now we are discussing about k is equal to 2. Previous stage means k is equal to 1. Say if the fuel cost for the first R, that is k is equal to 1, feasible states are 15, 14 and 12. If you find the fuel cost for this R1 for feasible states 15, 14 and 12. Suppose if the cost that we are getting is, actually if you solve the given problem, you will get the fuel cost to be equal to 10,211, 9,843 and 9,208. So we can see here in this previous stage, these two are the minimum cost. This has the maximum cost. So this can be neglected. So we are going to save only the minimum cost strategies. So those minimum cost strategies are going to be only 14 and 12. So that is this 14 and 12. That is very important. That is very, very important. So suppose two strategies, 12 and 14, which is nothing but L, are saved in previous stage. We can take that N is equal to 2. Then if you substitute for this F cost second R, feasible states are 15, 14 and 12. Our is 2. So you have to find for F cost 2, 15, min of 12 and 14. So P cost of K is 2, I is 15 S cost means transition cost. We'll see what is that transition cost is all about. P cost means production cost. So this is the fuel cost for the kth hour with ith combination. This is your production cost for kth hour with ith combination. And S cost is the transition cost. S cost is the transition cost, that is from state k minus 1 comma L to state k comma I. That is, what is this transition cost is, say for example, you have a load curve like this. You have a load curve like this. See, if I'm going to go from one state to the other state, say for example, I'm going to go from this R, say this is R1 to R2. I'm going from R1 to R2. So a transition is there. So during this transition, say for example, if here only some 2 units are running, 1 and 2 is running, say for example, I'm going to commit a third unit here, means if I'm going to commit this third unit from this period to this period, I'm going to start this third unit, so it will have some startup cost. It will have some startup cost. So that has to be included. That is what is called as your transition cost from this state. From this state, 1 and 2 units are committed, and then here the third unit is going to be committed with 1 and 2. With 1 and 2, the third unit is going to be committed. When I want to start this third unit, means you will have some startup cost that you are going to add. That is what is called as the transition cost from the previous state to our required state. So that you should understand. So that is your transition cost. So transition cost is S cost. So in this case, k minus 1 means you are discussing about, you are taken 2, k is equal to second hour, means 2 minus 1 is 1, the previous period. So first 1 comma, you substitute this 12, L is 12 here, is 2 comma 15, k comma I as it is, plus the fuel cost of 1 comma 12, that is first hour, the 12th state. So similarly, you should find f of 2 comma 15 for this 14 also. So you have to substitute instead of 12, 14, and you should find one more cost. So you will get for f2 comma 15, for state 12 you will get one cost, and for state 14 you will get one cost. So minimum of them you should take it. So that is going to be f cost of 2 comma 15. So minimum of these two states you have to take, that is going to be f cost of 2 comma 15. Similarly, you should find f cost of 2 comma 14. So 2 comma 14, similarly you substitute in this relation, you find it for 12 and 14, out of that you should take the minimum. Similarly, f cost of 2 comma 12, you will get 2 results for 12 and 14, out of that which is minimum you take it. So you will get 3 results. I will get 3 results. For these 3 feasible states you will get 3 results. Which has the lowest cost, you can save that. Which has the highest cost, you can neglect it. So again, if you come here, so this is a recursive algorithm. You can go on with the hours for all the periods and all the feasible states. You should go on checking these things. So f cost is the least total cost to arrive at state k comma I. Least total cost to arrive at state k comma I. P cost is production cost for state k comma I. And this S cost is the transition cost from state k minus 1 comma L to state k comma I. So if you put this recursive algorithm in a flowchart, you will get a flowchart like this. So I'll get a flowchart like this. So we can see in this flowchart, there's nothing but you start, and then for k is equal to 1, that is for the first hour, you find the f cost. There is nothing but the fuel cost for the R1 for all the feasible states. Mean of L, the previous state you can take, and then you can find this production cost of k comma I plus the transition cost of k minus 1 L k comma I. This you should do for all states I in Rk. So what are all the feasible states, you have to do it as you have seen in the previous thing, previous slide. So if you can see here, what is that we are going to do is, we have to do this for all the feasible states, 14, 15, 12 like that. So you should do it for all the feasible states, x is equal to all states I in Rk. Then you go for advance the Rk is equal to k plus 1. L is n feasible states in the interval k minus 1 or in the Rk minus 1. So n feasible states means, as you have seen in the example, we neglected one state, we took only 2 states which has got the minimum cost. So that is going to be our L. So which is n feasible states. In our previous example it was 2. So f cost of k comma I is going to be equal to mean of L production cost of k comma I plus the transition cost plus the fuel cost of k minus 1 comma L. So you do this for all the states. X is equal to state I in Rk. Save n lowest cost strategies. And then is k is equal to m. Is it the last R? For the given example, if it is 8 means last R means yes means trace the optimal schedule and stop. No means you go again, increment the R and then you proceed again. So this is how you should proceed with the dynamic programming approach for solving this unit commitment problem. So these things you can put it in a steps format and you can write it as an algorithm and you can explain this